Chapter 11-7, the power, the superposition, the principle. So in the AC circuit, the power superposition can be applied to analysis the circuit, because even though source is AC voltage or AC current, the electric circuit is linear. Therefore, to analysis the circuit, the superposition can be applied to the AC circuit. The problem is, when you calculate the power, then how to calculate the power? There are the many sources. For example, this is a problem. We have a simple circuit. This is resistor, is R. Or example is 5 ohm. Then we have two source, current source here, 1 and 2. So this is 2 amperes and this is 1 amperes. Then I want to solve the DC circuit. Then how to can you that? So because we can make the node, so this current, because this is 2 amperes, this is 1 amperes, so there will be 3 amperes. So therefore the voltage here is a VR. The VR will be RI on the 5, and current is 3, so 15 volt. Therefore the power R is VI. The V is 15 and current is 3, so the power is 45 watt. And IR is 3 ampere. So I want to solve this circuit with the superpositions. Then we can split this circuit as two sources. We have one circuit here, it's 2 amperes, 5 ohms, and another circuit is 5 ohms and 1 ampere here. So what is the voltage is VO and VR. VR1, this is a current IR1. In this case, VR2, this is IR2. Because IR1 is the same with 2 amperes. 2 amperes. Therefore, VR1 is RI1. And 5 and 2, so 10 volts. And how about this? IR2 is 1 ampere. So VR2 is RIR2, so 5 and 1 is a 5 volt. Therefore, the IR is superposition of IR1 plus IR2. Therefore, 3 amperes. And how about VR? Is VR1 plus VR2. So there will be 10 plus 5, 15 volt. This result is exactly the same with these solutions. So when you analyze the circuit, the voltage and current, then you can use superposition directly. Then two results is identical each other. But the problem is the power. When you calculate the power in these superpositions, then how about the power here? PR1 is VR1 and IR1. There's 10 and 2 is 20 watt. How about PR2? Is VR2, IR2 is 5 and 1 is 5 watt. So how about the PR PR1 plus PR2 is 20 plus 5 is 25. You know, that value is 45. This is not same with 45. So, in general, when you calculate the power, the superposition cannot be applied. When you calculate power calculation, superposition should not be applied in general. Because the current and voltage is a linear system in the electric circuit. But power is a kind of physically, the power is a voltage multiplied by the current. So multiplying of two variables is not linear in the viewpoint of the power. So we cannot use the superposition to calculate the power. So I have some simple review about why this is not proper to apply the superposition to calculate the power. For example, this is an example. I will give you some simple proof here. Why? Because when you say I is I1 plus I2, and power is I square R, therefore all I1 plus I2 square. That means all I1 square plus I2 square plus 2 I1 and I2. So when you calculate the average power average is integral for one period d pt dt. So we apply that variables here, all t from 0 to t, I1 square plus I2 square plus 2 I1 and I2 dt. So that will be all over t 0 to t I1 square dt plus all over t from 0 to t I2 square dt plus 2 all over t 0 to t I1 and I2 dt. So I know that this is exactly same with the P1 plus P2 plus we have one more things. So the P1 is calculated by from the source 1, and P2 is a power from the source 2. So the total power is the same with P1 plus P2. This is, if they satisfy this condition, then we can use superposition. So to satisfy P average should same with the P1 plus P2. That means should be 0. If that term is 0, then when you calculate the power, you can use the superpositions. So we want to find out what kind of condition you can apply the superpositions when you calculate the power. So you need to check let the expression of I1 is the magnitude of I1 in cosine m omega t plus pi, and I2 is I2 cosine, and more general expression of the frequency, so n omega t plus theta. Then to calculate this, so we need to check it from 0 to t. I1 is cosine m omega t plus pi cosine n omega t plus theta and dt. So you know that this is very simple problems. There will be 0 when m and n is different, but this is value is cosine phi minus theta when m and n is equal. And finally, as a result, what's the meaning of m, and m is not same with n? Then superposition can be used to calculate the power. So therefore, 12 over t, integral from 0 to t, I1 and I2 dt will be 0 when the m is different n, or will be r I1 and I2 cosine phi minus theta when m equal to n. I mean, what's the meaning of this? The frequency of two sources as are different. What's the meaning of that? The frequency of our sources are same. So the power can be applied, power superposition can be used when the source's frequency is different, but there are same frequency, then we cannot use the power superpositions. So that's your reason. In this case, what's the frequency of that? This is a zero frequency. Frequency is 0. Frequency is 0. This frequency is 0. So same frequencies. Then we cannot use the power superposition here. But if you have different frequency, then you can use it. So, and finally, I can summarize that. It's important. Superpositions can be applied like to to find voltage and current in the electric circuit. In that case, we don't need to care about the frequency. Here is don't care of frequency. How about superposition can be applied to calculate power. Only there are different frequency source. This is a summary of that. So I will give a simple example here. Example is 11.7 and 1. We need to find the average power by 6 ohm resistor. So we have circuit here, and plus minus, cosine 3t, and resistor and inductor, and we have another source here, plus minus. And then there will be, this is VA and this is VB, and there is a 4 cosine 40. So omega 1 is 3, omega 2 is 4. So in this case, you need to divide the circuit with superposition. Why? Because the frequency is different. So the first circuit is, we have one source here and 12 cosine 3t, and resistor, inductor, and short circuit here, because the voltage is short circuit. So this is 6 ohm. This was 6 ohm and 2 heli. So in this case, that variable is 12 and 0, and here omega govern the frequencies, the 3 radian per sec. So this is a 3, and this is J omega L. This is J omega is 3 and L is 2. So there will be J6. So we need to calculate the current I. The I1 is, source is 12 and 0 degree, and impedance is 6 plus J6. So there will be 12, 0 degree, and 0 with 2 and 45 degree. So there will be minus 45 degree. And how about the current, the second circuit? In second circuit, we have another things here. We have source here. But this is a 4, omega is 4. Here is omega is 4. There is a 4 and 0 degree, and this is 6. In this case, J omega L. J omega is 4, L is 2, so it is J8. So here we will find the current here. So we define this current is, I will define the current is I2, I1. So I2 is the reverse of this current. Actually, this current is here. I put it like that. This current is source is a 4 and 0, and impedance is a 6.8. So I2 is 1 and 180. Why? Because direction is reversed. And 4, 0, 6.8. So the result is 0.4 and 126.87. So what's that? I1T was 1.414 and cosine 3t minus 45 degree. And I2T was magnitude is 0.4 and cosine 4t and plus 126.87 degree. So how to calculate the power? The power in this case, because the frequency is different, the power is P1 plus P2. So you know that the word is P1. And P1 is half R magnitude square 1 plus half R magnitude square. So half R is the same as 6, and I'm sorry, oh, it's long, I'm sorry. And half I square R, so I1 square R plus half I2 square R is half I1 is 2 square R is 6 plus half 0.4 square and 6. So that result is 6.48 watt. But in the case of, there are two sources here. I mean we have a same circuit. We have the same circuit. But the frequency changes. This is not 3. This is not 4. This is 4. So we have the same frequency. So we have divided this circuit is the superpositions. So first, I'll use it on the blue lines. First, here, here, here. This is omega is 4. It's 12, 0, and this is 6, and there is the 8. And define this current is I1. So I1 is 12, 0 degree and 6.8, so that will be 1.2 and minus 53 in degree. So there is 0.72 minus J 0.96. How about the second source? It's short circuit L, another source here. We define this is I2. So this is a 4 and 0 degree and 6 and 0, 8. I2 is the reverse, so minus 740 and 4 plus and not 4. 6 plus J8. So that result is 0.24, 126, and 83 degree. That will be minus 0.24 plus J 0.32. So what is I? I is I1 plus I2. Therefore, the result is 0.48 and minus 0 J 0.64. So it will be 0.8, angle is minus 4313 degree. So what's the meaning of that? Then from there, you can calculate IT is I1T plus I2T. It's very complicated problems, but anyway, we can solve that. Here is maybe from here, I1T is 1.2 cosine 4T minus 53 and 17. And from here plus 0.4 cosine 4T plus 126.83. So it will be reduced to the 0.8 cosine 40 minus degree. From here, we can calculate the power is half Im square and R. So half 0.8 square and 6 1.92 watt. So it's perfectly different. I mean, this is 6.48, but when you have the same frequency, the result is different. So when you calculate the voltage and current, you can use the superposition as you want. But when you calculate the power, then you can use the superposition when the frequency is totally different. If there are same frequency source, then you cannot use the superposition. That's because when your frequency is the same, the power is non-linear. The superposition is a property to be applied to the linear system. Next, this is chapter 11 and 8, the maximum, the power transfer theorem. This is about how to transfer the power as much as possible. I mean, we have a source here, and we call it VT, and we have line impedance here. Actually, I don't know what's the value of that, but there will be line impedance. It's called GT, and we have a load here, GL. And actually, the transmission line is a given. You cannot change the transmission line given. So GT is a given values. You can fix it. We can modify the transmission line. But my target is, I want to get the maximum power from the source. So we want to receive the maximum power. from the voltage source. Then what should we do? What could we do? So that is the maximum power transfer theorem. We can only modify the GL. We can design the GL because this is a load. So our target is that we get the maximum power from the source. So I will modify the GL. So how to design the GL to get a maximum power from the source? There's a problem over this. How the GL should be designed for maximum power. That's your target to do in this chapter. To do that, we need to calculate the power to receive the GL. So what is the load power? The power is P is half and current square and RL. I don't know what is that the value of the RL, but anyway. Then we need to calculate current at first. We define this as current is I. I is Vt divided by Gt plus GL. Then let GL, I don't know what is GT, but we make a general representation of GT is RT plus JXT, and we make a general expression of GL is RL plus JXL. So that will be represented as Vt is RT plus RL plus JXT plus XL. Then we calculate power again is half magnitude of current square and RL now from here we can calculate the current magnitude. How can we do that? That the magnitude of current will be Vt square and the square is RT plus RL square plus XT plus XL square. So current magnitude it will be Vt root RT plus RL square plus XT plus XL square. So I'm insert that value here. So that result will be half, rewrite here, RT plus RL square plus XT plus XL square Vt square and RL. That's your power that can be received in the active power received from in the source. So our target is maximize to I will use different color to maximize average power P. Then what should we do? Then to maximize the power, then that value is fixed. I mean, we need to check it. We need to rewrite here. The P was half T square RL RT plus RL square plus XT plus XL square. The fixed value is Vt. This is a source, and RT and XT is fixed. The control variable is RL and XL. Then to maximize the P, we need to minimize this term. Denominator should be minimized. So to do that, this is positive values, they can be reduced to this 0. Therefore, if we make XL is minus XT, then this can be achieved. Then the remaining thing is P can be half RT plus RL square and Vt square RL. And to maximize to P, and control variable is RL, so to maximize, then what should we do? Then it will be 0. And the result is round RL, round P is half RT plus RL square Vt square RL will be 2 RT plus RL square Vt square minus RT plus RL cubics and Vt square and RL should be 0. So that will be 2 RT plus RL cubic and Vt square RT plus RL minus 2 RL will be 2 RT plus RL cubic Vt square and RT minus RL. That should be 0. But to do that, what should we do? RL should be RT. Therefore, we have two conditions. XL should be same with minus XT, and RL should be same with the transmission impedance of R. So, therefore, GL should be RT minus JXT. This is a GT's conjugate. If we define this impedance, this load impedance, the given GT and VT, the load receive the maximum power. From voltage source. This is the maximum power transfer theorem. GL should be same with GT's conjugate. This is example of the maximum power transfer theorem. Example 11, 8 and 1. To find the load impedance that transfers maximum power. So we have source here, and this is some impedance in the transmission lines, and we have a load here. So transmission impedance is 5 minus J6, and this is a load impedance GL, and the source 10 and 0 degree. So what should we do to transfer the maximum power actively, especially maximum active power to the load? To do that, GL should be same with the GT conjugate. So therefore, GL should be 5 minus 6 conjugate is 5 plus J6. So then, what is the maximum power? Then we need to calculate the current here. We find this is current. Then current is 10-0. This is voltage, and impedance is GT plus GL. So that'll be 10, and GT is 5 minus J6, and GL is 5 plus J6. So that will be 1 degree ampere. So we need the power from the source. Is compressed power is half VI conjugate. Half V is 10-0, and current conjugate is 1-0. So there'll be 5. That's all. So there are no active power is 5 watt, and the reactive power is 0 watt. So then we need to calculate each power consumed the GT and GL. So I want to calculate the GT. ST is consumed by GT. So it will be to calculate that, we need to calculate this variable at first. So we need to define this is a VT and this is a VL. At first, we need to calculate the VT and VL at first. So VT is the voltage drop caused in transmission impedance GT. So there will be VT is GT and current. So GT is 5 minus J6 and current is 1 degree. Therefore 5 minus J6 volt is a GT, and the VL is voltage here, and the load voltage is GL and I, and GL is defined 5 plus J6 and I is 1 degree. Therefore 5 plus J6 volt is a GVL. So we need to check it that is right. So this is Vs, the sum of Vt and Vl. And Vs was the sum of Vt and Vl. Vt is 5 minus J6. Vl is 5 plus J6. There will be 10. So this result is exactly same with the given variable. So it's right. Then I need to calculate the power consumed by transmission line in ST first. ST is half Vt I conjugate, then half Vt was here. 5 minus J6, and current is 1 and 0. Therefore, 2.5 minus J3. How about the SL is a complex power consumed in the load. Half VL I conjugate, then half VL was that variable, 5 plus J6, and current is 1 and 0 degree. There is 2.5 plus J3. So that value is this is a average power consumed in load. So that is a average power consumed by the transmission line in GL. So the source support the 5 watt. So some of them is 5 watt. Then in this here, the source does not provide any reactive power, but transmission consumed minus 3 var and load the plus 3 var. So what's the meaning of that? That means there are some between the transmission line and GL, there are the interchange of reactive power between the GT and GL. So, but the source does not give any the reactive power. We call this oscillation. We will discuss about the oscillation in the later. No, 11 and 9, the coupled inductor. And this chapter is quite important. So, but I will introduce about the transformer. We discuss about the electric circuit. The electric circuit consists of the source and RLC and OPM. That's all. And we're adding one more thing here today. That is a coupled inductor. This is very similar with transformer. We will discuss about the transformer later. And anyway, the coupled inductor is, inductor is a kind of a magnetic device. And this device is very simple, has a very simple structure. We already know about the capacitor and inductor. Capacitor stored energy in the electric field. Is stored energy electric field. And inductor store energy in magnetic field. The structure of capacitor is very simple. It is a plate. And there is a plate. It's a conductor. And there are some store the plus charges here. In between two plates, there are no current path, there are no conductor. But they consist of, they are filled with the no conduction materials. So there are no current path here. Because of these charges, there are minus charges stored in here. Then because of these charges, and they are stored in some field, E field like there. It's an E field. The energy is stored in the form of the E field. We call this a capacitor. And in inductor case, and there are some wires in the core like that. And the coil is connected in this way. Actually. Then current flowing through these coils. Then because of this coil, there are stored some magnetic field here. Here, 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 here. In this way, in the same way there. So totally the field is stored in this way here. Like kind of a solenoid. So if there are some current, then some magnetic field is B field is stored in the coil. The energy is stored in the B field. So this device we call the inductor, and this device capacitor. The coupled inductor is kind of an inductor, but there are very important characteristics between the B field and the current. The electric variables. To understand that, we need to know about the Faraday law. And what is the Faraday law? Faraday law means, there's some coil here, this conductor coil. Then there are some magnet here. So because of the magnet has a magnetic field in this way here. But in this instant, in the loop, in the coil, there are no magnetic field because the distance of here is long. But in some reason, I don't know what is that, but some reason, the magnet, the magnet is going into here, move that. Okay. In some reason, I don't know the exact reason, but magnet move in here. It's just like that. In this instance, in the loop, the flux is increased. We call this magnetic field is a flux. This is magnetic flux. By the phi. In this instance, in the air, no flux. But the magnet moving here, in the there, flux increase. The further law means in the loop there are some fluxes variations. Then because of this variation of flux between this port and this port, there are some voltages induced. E dt d flux. Especially the term number is 1. This is 1. This is a Faraday law. In Korean, 전자기 유도 법칙. This law discusses about the relationship between the electric circuit and the magnetic circuit. So in this case, the flux variation, magnetic variable, flux variation causes the electric variable is voltage. This is a Faraday law. In Korean, or like in Korean. So this is a Faraday law, and if there are many turns are there, first 1, 2, 3, in this way here, maybe this n turns. In the same way, there are the magnet, then the flux happen in this way. Because of this flux, the T d phi has induced the voltage. But there are n turns. Each turn has a voltage in this amount. So total induced voltage E is n times dt d phi. This is the final form of the Faraday law. And you can read right here is dt d n phi. Here you define n phi is the lambda. Lambda we call this as a flux linkage. In Korean, 쇄교 자속. The flux caused by other element is linked with a coil. but the coil has n-turns, so linked is n times. So linked variable is n phi. So you call this a lambda, this is a flux linkage. The coupled inductor is a magnetic device that consists of two or multi-turn coils and wound on a common core. We call that is the coupled inductor. I mean, there are some coils. This is this is a core. This core it consists of the iron or silicon steel, it's like that. I mean, this is a core. And generally, core is consists of silicon steel, iron, the two things, and so core is amount here. For example, goes like that. Another term is so two cores are wounded in the common core, and this turn number is N1. This turn number is N2. Then there are some voltage connected in this way. This is AC, we call this a V1. Then current flowing through the first winding. This is a I1. Then there happens some voltage here. This is a V2 and flowing flow the current I2 in this way. When core is silicon steel and iron, this is a very high permeability. In Korean, 투자율. I mean, the high permeability material is, the flux is very well established in this material. So we call this structure is coupled inductor. In other words, it for a transformer.